All right, let's get this started here. This is section 9.3, and this is all about multi-step methods. So to preface this a little bit, we have to understand a little bit about the previous sections. So 9.2 is pretty important within doing 9.3. So within 9.2, these are all methods for solving differential equations. The range kata methods are a thing about 9.2. So these are pretty important to understanding these. So the RK4 value or method is something that we're going to need to know. So the range kata methods are four distinct different methods that they're pretty commonly used. The first is a Euler method, and the fourth is a method that is very common and we will be using here later. The middle ones aren't super important to us at the moment. So to do the range kata methods, just get straight down into business because you have to know this as background. So RK4 is the fourth one, fourth range kata method, and these are the important equations. So to get these different 4K values, what you need to compute the y values here, I'll show you in a second. You have the x of n, y of n, and these are your initial conditions. So x of n is usually going to be 1, or no, sorry, x of n is usually going to be 0 at the initial condition, and every time it will go up by h. But like these four will all be 0 for the first part. Then your y is going to be your given. So in a problem, you'll see that later. So these different parts give you the different k values. And then to go back in, you put those into this equation here, and your h is your step value. So we'll have examples of this later. And your y sub n is your initial value, and that gets you your y sub n plus 1. So this will be helpful in later issues here. So solving RK4 for use in 9.3. So here's kind of the general steps you're going to need to know for this purpose of 9.3. So to solve these, find the k values and substitute into the equation to get a y n plus 1 value from the initial condition. Then you have a y value at your different points. So that's going to get you this, going through it once is going to get you your first y value. To get the next y value, you're going to have to go through it again all the way through the whole process to get that y sub n plus 2, essentially, if your n is your initial 0 or your whatever. This will all make sense when it comes together in a little bit, if it doesn't make any sense now. So to do that, you have to go through the whole system one more time to find y2, and to find y3, you use the y2 values and you go through one more time to get y3. So you're going through the whole process 3 times where you are finding your k's and using this equation down here to figure out the y sub n plus 1 or y sub n plus 2, etc. So now we're going into the actual gist of 9.3. 9.3 is all about multi-step methods. The single step in starting methods is what we're used to now. It's like Euler's method, the Runge-Kutta method, and the multi-step continuing methods is what we're going to be learning. The one we're going to specifically be talking about is the Adams-Bashforth-Moulton method. So a single step are based on the successive value. So like y sub n plus 1 is based on y sub n. Multi-step methods are based on several different values, which makes it interesting when you have a data table or things like that, especially when it comes to applications. So mainly this method is used to approximate values within differential equations. So say if you wanted to approximate y sub or y of 0.7 of this equation and you have an initial condition, the Adams-Bashforth-Moulton method will help you do this in a way, just with a little bit of computation. So in the real world, the applications of this method are used in control theory a lot within engineering to solve differential Riccati equations. We're not going to really talk about those, but it's all about optimal control, filtering, estimation, decoupling, etc. So the Adams-Bashforth-Moulton method, it allows for an explicit computation of the approximate value in time with regards to other instants in data. So you get an instant in time approximate value, and you can do that if you have a little bit of info about other instants in time, but it is an approximation. So there's two parts to the Adams-Brasforth-Moulton formula. So this part here is the Adams-Brasforth formula, and it is the predictor part of the 9.3 section of the method. So the predictor is this long equation here. Oop, my bad. This long equation here. So this y sub n is your initial condition. All of these are found by this down here. So y sub prime of n, or y prime of n, is equal to your initial x and then your initial y into your initial function that you'd be given to find the estimation of. And then it goes on with all of these things for n is less or greater than or equal to 3 in this case. So this gives you a y asterisk or y star n plus 1. And then we can take this and go into the second part of the second part of the equation of the method, and it's the Adams-Moulton corrector part. So it's corrector, and you insert the predictor into the corrector. So you insert it right here, essentially. Your x of n plus 1 is going to be your value that is based on your initial condition and your h. Your y sub n plus 1 is going to be what you just found. So then you plug that back in your equation and you get a y prime n plus 1. And that goes here. And these other things we talked about how to find earlier. This h is your stepper function, or how much you're going up each time. Y sub n is the initial condition. And this gets you your ultimate value. What you're wanting for is your approximation of y sub n plus 1, and it'll all work out that way. So note that these formulas mean the values have to be known between y sub 0 to y sub n just to be able to obtain this. But there's ways to get that with the method we were talking about earlier. So let's talk about an example here. Let's dive right in. So here's an example of y prime is equal to x plus y minus 1. This is at y of 0 is equal to 1. If the step size is 0.2, approximate y of 0.8 using the RK4 method. So using the RK4 method is not what we're, but using the RK4 method, we are going to find the different y's that we're going to need to then apply the Adams-Brasforth-Moulton method. Tongue twister. So to do this, we talked about it a little bit earlier, but because it's not in this section, I'm not going to spend a whole lot of time on it. You can pause the video and see the work here if you would like. But essentially, you go through the k's, find the k. K's is the different value, plug it into your equation here, and essentially you go through this and you get your n plus 1, and this is your just y sub 1. And then after you have y sub 1, you can use that and the next value, which is 0 plus the h, you find y sub 2 if you go through this whole thing again, and then to find y sub 3. Okay, so after you find these y1, y2, y3s, we're going to go to the next part here. Did I go too far? No, I did not. Oop. Okay, so after you got this point, you know that you have corresponding x values. They're going to be plus h every time. So you have 0 is first one, 0.2, and then 0.4, and then 0.6, and you're looking for 0.8, if that makes sense. So then we're going to go into this equation. We're going to find our initial here. Oop, one too many. So we're going to find our initial here. This goes into that first part of finding what these values are, because we need to find those in order to plug into the method. So you go through this, pretty simple. You just have your initial conditions, you put it in the equation that you're given, which you saw a few slides ago. And then you can go through here, get to the next ones based on what you have and all of this stuff, and it goes all together. These y's are going to be what we found with the first the RK4 method or the RS4 method, and then these are going to be these here. So after we get to that, we have this equation. We can come into here, and so this is your ultimate equation, and you can plug each of these values in to get your ultimate y star of 4. Okay, so now after that, we go to that. So that was the first part. That was the initial stage, the stage before the corrector. Sorry, I'm drawing a blank. But before the corrector, we need to find this thing we were talking about here, the y prime of 4. So which is y prime of the s plus or the plus 1. So then you got here, you got your f of these, and this is what you just found here, which is that, and then your x of 4 is your 0.8, I believe. Yeah, oop, mouse. Okay, yeah, your y sub 4 is your 0.8. So you have this, and then you go into your corrector, and in your corrector you can actually get to the final answer from there. So your y sub 4 is equal to y of 3 plus, and then you know all these values now because of what we just did, and these are what we found out initially, and you can get to your ultimate answer. Sorry if we're going through this a little fast, but so this can be checked by an analytic analysis to verify and compare the two systems and check the value, but also know that this is an approximation, and it is made so it can be an approximation and done in a specific way. So now we steps to solve this kind of problems. So there's some main steps here. Oop, one too many again, sorry. So there's some big steps here to follow in general to get to the equations we're looking for. You want to find that, sorry about this typo here. So you want to find the x and y values, y1, y2, and y3, given your initial conditions in your equations. And you do this using h and x and RC, and using the RC4, the initial things we're talking about from 9.2 for y. And then you want to plug these coordinates into the initial given equation, and you find those values, and you insert them into the predictor formula, which then will give you a y star value. Then after that, you can compute this, the y sub prime of n plus 1, and then you can go into inserting all of the knowns in the corrector formula and solve for your desired outcome of prediction, yeah, for your prediction, or what's the word? For the, yeah, for the, you know what I'm talking about, I think. Okay, going to the next part here. So the stability of numerical methods here. So if numerical method is stable, small changes in the initial condition will result in small changes in the computed solution. So essentially, if as S changes farther away from that, or as the step gets bigger, if the error gets bigger, that's probably a good thing. It means it's more stable than unstable. So if large changes occur over small changes in the initial condition, then it is unstable, and it is pretty inaccurate when you're going for those estimations. That's the word. Okay. So the less stable, the less valid and accurate this whole method is. So the less accurate the final approximation. One way to check stability is to see if the error increases with step. And if it does, it is stable as the step size increases. And if it is not, if it is increasing, or is decreasing in error, or is increasing in error as the step decreases, the step size decreases, it is unstable. So next part here. So some of the important parts about, or general gist of the multi-step method here, is single-step methods require a lot of manipulation on the sides of the equation. So with the multi-step method, it requires really only one change per computation, and it's finding those different values and just plugging it in. So it makes it easier to use in programming language, and it can be used much faster and cheaper if there's a stored values. So especially when you're doing analysis of things, it makes it pretty easy because you have a basis of values stored and that kind of thing. So thank you guys for listening. Hope this helped. If you have any questions, you can ask me or let me know. Adios.